Hello and welcome. In this lecture, we will talk about bandwidth efficient AM, specifically single sideband suppressed carrier amplitude modulation. Previously, we have talked about double sideband with carrier and double sideband suppressed carrier modulation. They were not bandwidth efficient. In this lecture, we will talk about single sideband suppressed carrier. This is bandwidth efficient. In a moment, we will know why this is called bandwidth efficient amplitude modulation. In the case of DSB-SC or DSB-C, we know that both upper sideband and lower sideband is transmitted. That's why the bandwidth requirement was double compared to the message bandwidth. If the message bandwidth was B Hertz, then the modulated signal bandwidth was twice B. Specifically, this is the reason why they were called bandwidth inefficient, because the message requires only B Hertz of bandwidth, but when we are transmitting it as a modulated signal, we are using double of that required bandwidth. So how we can solve this problem? There are multiple ways. One of the popular ways are single sideband suppressed carrier modulation. In this modulation technique, only USB or LSB is transmitted, not both. That's why the bandwidth requirement is now B Hertz instead of 2B as it was in DSB-SC. That's why spectral efficiency is improved by 100%. So let's see some figures to get a better insight. This is a message signal in frequency domain. This is the baseband signal. So when we are using double sideband suppressed carrier modulation technique, this whole bandwidth will be transmitted to FC and minus FC. FC is obviously the frequency of modulating signal. So here we can see that the spectrum is shifted to FC and minus FC. Obviously the height of this spectrum will be half than what it was in the original spectrum. And we all know that this portion here and this portion here, these two combinedly make up the upper sideband, and this portion combinedly make up the lower sideband. So in the consecutive figures, these upper sidebands and lower sidebands are shown separately. In the upper figure, we can see there are only upper sideband, this one and this one. And in the case of the lower figure, we can see there are only lower sideband present, this one and this one. So when we are transmitting a signal in this form or this form, then our bandwidth requirement is half of the requirement in this case. Here you can see the bandwidth requirement is equal to the original message bandwidth B. Now we know what we need to transmit in the case of single sideband suppressed carrier modulation technique. But the question is how we are going to achieve this type of spectrum. This question will be answered in a moment, but let's first understand how this spectrum or this spectrum alone is enough to reconstruct this shape. So let's consider coherent detection. Just to remind you, coherent detection is the type of detection where we multiply the modulated signal with the carrier once again. So this was our USB signal, only the upper sideband components are present. Now when we will multiply this signal again with a cos wave of FC frequency, then this component will be shifted by FC upward and downward. So it is presently in FC frequency. So after multiplying the cos wave, this spectrum will be shifted to FC plus FC, which means 2FC, and FC minus FC, which means 0. In a similar fashion, this spectrum is at now minus FC frequency. So when we will multiply this spectrum with cos carrier of FC frequency, half of this spectrum will be shifted to minus FC, which means minus 2FC, and half of the spectrum will be shifted to minus FC plus FC, that means 0 frequency. So you can see that after multiplying with a cos wave of FC frequency, we are achieving this whole spectrum. Now we obviously know what to do after that. If you use a low pass filter, then this spectrum here and this spectrum here will be suppressed, and we will be left with only this thing, and obviously this is the shape of the message. That's how SSB signal is transmitted and recovered. But now the question is how we can create the USB or LSB signal for the original message spectrum. Before diving into the detail, let's talk about a new concept, that is Hilbert transformation. You don't need to know the details of it, just we want to know what is happening when we are Hilbert transforming some signal. Let's say we have a signal XF. Obviously this signal is XT in time domain. In frequency domain it is XF. This is an arbitrary signal. So when we will Hilbert transform this signal, it will become x of hf. X of hf is the Hilbert transformed version of xf. So what is xhf? Simply, xhf is the multiplication of the original spectrum xf with minus j and sgn of f. Now the question is, what is sgn of f? It is simply the sign of f. This sign means the positive or negative sign. So when the frequency is positive, sgn f is plus 1. When the frequency is negative, sgn f is minus 1. Simply the sign of the frequency. I am repeating once again. This sgn f is plus 1 when the frequency is positive, and sgn f is minus 1 when the frequency is negative. We will get to see the visual representation of sgn f in the next slide. So simply xhf is minus j xf sgnf. So if we separate the xf part from it, we will be left with minus j sgnf. This minus j sgnf is essentially hf, or the function of Hilbert transformation. Thus hf is minus j sgnf. We already know when f is greater than 0 or the frequency is positive, then sgnf is plus 1. So hf becomes minus j, and minus j, we can represent this minus j in polar coordinates in this fashion: 1 into e to the power minus j pi by 2. When frequency is negative, sgnf is minus 1. So hf is actually minus j times minus 1, which is j. We can represent this in polar coordinate in this fashion: 1 times e to the power j pi by 2. That means when we will multiply our xf with hf, amplitude spectrum will be unchanged, because the amplitude part of this Hilbert transformation function is essentially 1. So when we will multiply this with xf, the amplitude spectrum will be remain unchanged, but this will affect the phase quantity, and there will be actually a minus pi by 2 phase shift. So a Hilbert transformer is an ideal phase shifter that shifts the phase of every spectral component by minus pi by 2. That is all we need to know about Hilbert transformation. Let's carry on our discussion on SSB-SC. Here is our message spectrum. When we want to achieve SSB-SC spectrum, we essentially need to separate the positive half and the negative half of this message spectrum. Let's say this is m plus f. M plus f is denoting the positive frequency part of this message spectrum, and this is m minus f. M minus f means only the negative frequency part of this frequency spectrum. Okay, so we want to achieve this m plus f and m minus f, and the input is actually the whole spectrum mf. As I have already told, that sgnf is such a signal that is plus 1 when the frequency is positive and minus 1 when the frequency is negative. Another signal we will be using here is unit step function. We already know what is unit step function. It is 0 for all negative frequency and 1 for all positive frequency. Now recall from the previous slide, the Hilbert transformed version of any signal was the spectrum of that signal multiplied by minus j sgnf. If we are considering this mf signal, then mhf is actually minus j mf sgnf. So if we just divide both parts by minus j, then this part will be mf sgnf. It will be equal to mhf by minus j, and we all know from the property of j that when something is divided by minus j, it is actually same thing if we multiply it by only j. So mhf by minus j becomes j into mhf. So now let's continue our main discussion, how we can get m plus f from mf. So m plus f is basically mf multiplied by uf. It is very simple. If you multiply this signal with this signal, then all the negative frequency components will be suppressed, because it is 0. 0 multiplied by anything is 0. So it will become 0 in the negative frequency part. But as in the positive frequency part, uf is equal to 1. So in the positive frequency, the shape of m plus f will be exactly like mf. So now we can understand why we are getting m plus f from multiplying mf and uf. This uf can be generated from this sgnf. How? Let's say I am adding 1 to this sgnf. If I add 1 to sgnf, then whole signal will be shifted upwards by 1. So this minus 1 line will be shifted to minus 1 plus 1, that means 0, and this one line will be shifted to 1 plus 1, that means 2. So the signal will be something like this: 0 in the negative frequency part and 2 in the positive frequency part. That is similar to UF but not exactly UF. What we need to do to get UF from that signal? Simple. You just divide it by 2. Then this 0 divided by 2 will be 0, and here it was 2. 2 divided by 2 will be 1, and so we will achieve UF. That means UF is actually half of 1 plus SGN F. That's what we are getting here. MF is MF and UF is replaced by half of 1 plus SGN F. Now we just multiply this MF with both the parts. So this part will be, half will be common. So this part will be MF and this part will be MF SGN F. Now as we know, MF SGN F is JMHF, so we can replace it with this. So ultimately M plus F is half of MF plus JMHF. In the similar manner, we can achieve M minus F. To get M minus F, we have to multiply MF with the reflected version of UF, that is U minus F. We can similarly derive U minus F from SGNF. I would encourage you to derive U minus F from SGNF, but I have already written it there. So this will, M minus F will be, so M minus F will be MF multiplied by half of 1 minus SGNF. I highly encourage you to determine how U minus F is 1 minus SGNF. It is very easy. Try it on your own. So again, if I take half as common and multiply both the parts with MF, I get half of MF minus MF SGNF. Now as MF SGNF is J of minus J multiplied by MHF, so I can replace it here, and finally my M minus F is half of MF minus J MHF. Now this is our USB spectrum. Let's take a look at this USB spectrum carefully. There are two components in this USB spectrum. First one is this one. This one is basically an M plus F frequency component but shifted to FC frequency. And this is actually M minus F frequency component but shifted to minus FC frequency. As this is shifted to FC frequency, we can write this as M plus F minus FC. That is because this was our M plus F. If we shift it to FC, then it will become M plus F minus FC. Minus FC means it is right shifted. In the similar manner, this is M minus F plus FC. Similarly, we can analyze the spectrum of LSB spectrum. Here it is M minus of F minus FC and M plus of F plus FC. Let's first derive the equation for USB spectrum. Phi USB F is actually this spectrum plus this spectrum, M plus F minus FC plus M minus F plus FC. We already derived the equation of M plus F. We just replace it here. M plus F was half of MF plus J MHF. We are just replacing it here. Only difference is in the previously it was F and now it will be F minus FC. So half of M F minus FC plus J MH F minus FC. Plus we also derived the equation of M minus F. It was half of MF minus J MHF. Here the only difference will be, instead of F, we will write F plus FC. So half of M F plus FC minus J MH F plus FC. So here we can see there are one M component here and one Hilbert transform version of M here. One M here and one Hilbert transformation version of M here. We can take both M versions together and both Hilbert transform versions together. So it will be half of M F minus FC plus M F plus FC. And then if we take J common, it will be J by 2 M H F minus FC. As I have already mentioned previously, multiplying something by J is actually dividing it by minus J. So we can write this as minus 1 by 2J M H F minus FC. Similarly, we can take minus J as common from here, and this part and this part will make this whole part, that is minus 1 by 2J MHF minus FC minus MHF. If this feels a little bit confusing, I would just encourage you to apply the rules of J and you can easily derive this one. Now what does this two thing means? Let's take a look at this part. M F minus FC plus M F plus FC. This seems similar, right? What does this mean? This means a spectrum, it is shifted to FC frequency and minus FC frequency. and also the amplitude of both the spectrum components is half. Now we know this actually means multiplying the original signal with cos wave of FC frequency. That means if the original message was empty in time domain, we can say that this means empty cos omega ct. Similarly, 1 by 2j mhf minus fc minus mhf plus fc, this actually corresponds to the case when a time domain signal is multiplied with a sine wave of fc frequency. That's why we can write this as mht sine omega ct. Obviously, mht is the time domain signal of capital MHF. You can cross-check this from the Fourier transform table. You can see there what is the frequency spectrum of a signal multiplied by sine wave. In the similar manner, we can also determine the equation of phi LSB in time domain. I would encourage you to do this on your own. You may see this in a future assignment too. So if you do this now, it will be helpful for you. So our phi SSBT is actually one of these two. These two are very similar. Both has mt cos omega ct in it and mh sin omega ct in it. In the case of USB it is minus, and in the case of LSB it is plus. So we write them together as this fashion. Phi SSBT is mt cos omega ct minus plus mht sin omega ct. Here mt is original message signal, mht is the Hilbert transform version of the message signal in time domain. Now the question is how we can achieve this SSB signal with practical circuits. We need a circuit diagram for it. Here is a circuit diagram for achieving the SSB signal. This is called the phase shift method. Same thing we are learning so far. So first we have the message, and the message is divided into two parts. The same message is directly passed to a DSB-SC modulator. DSB-SC modulator simply means multiplying with cos omega c. So you can see that mt is coming from here and cos omega c is coming from here. So the output of this modulator is mt cos omega ct. The other version of mt is then passed through a minus pi by 2 phase shifter. As I have already mentioned, minus pi by 2 phase shifter is essentially a Hilbert transformer. So this block Hilbert transforms this signal and mt becomes mht in the output. Similarly, cos omega ct is passed through a minus pi by 2 phase shifter block, and we already know that if a cos wave is shifted by minus pi by 2, it becomes sine wave. So this modulator or multiplier again multiplies this mht and sine omega ct. So the output is mht sine omega ct, and then both the signals from up and down comes to a summer. Then we have two options. This is always plus, but we have an option in this case. If we want the USB signal, we will choose the minus sign. If we want the LSB signal, we will choose the plus sign. And finally, we have got the SSB signal as the output of this summer. There are obviously other methods of achieving SSB-SC. One of them is selective filtering. That means this is a DSB-SC signal. So if I somehow filter this portion out using a high pass filter, then we can achieve this. So this is another method of achieving SSB signal. So that is selective filtering method. Finally, SSB-SC demodulation. I have already mentioned how to demodulate SSB-SC signal, that is coherent demodulation or coherent detection. Very simple. Multiply the SSB signal with cos omega ct. So let's see what happens. Phi SSBT actually means this one, mt cos omega ct minus plus, depending on LSB or USB, mht sin omega ct multiplied by 2 cos omega ct. There is additional, it will help to get the raw version of the message. If you just skip these two, this will not create any problem. So this 2 cos omega ct is multiplied with this part, and this becomes mt cos omega ct into 2 cos omega ct. That means 2 mt cos square omega ct. And now we know 2 cos square omega ct is actually 1 plus cos 2 omega ct. So if I multiply 1 plus cos 2 omega ct with mt, it becomes mt plus mt cos 2 omega ct. Then this 2 cos omega ct is multiplied with this part too, mh sin omega ct multiplied by 2 cos omega ct. So it will become 2 mht sin omega ct cos omega ct. We now know the formula of sin 2a. Sin 2a is actually 2 sin a cos a. That means 2 sine omega ct cos omega ct is actually mht sine 2 omega ct. So we have three components here, mt cos 2 omega ct and mht sine 2 omega ct. You can readily understand that these are all high frequency components, so we can actually get rid of them using a low pass filter, and our final output after the low pass filter will be mt. That is how we can achieve SSB-SC demodulation. Amplitude modulation is done. We will conclude our discussion on amplitude modulation with a quick overview and comparison between DSB-C, DSB-SC and SSB-SC. So in the case of DSB-C, modulation process is simple. We just used some diodes, some filters, and that's all. In the case of DSB-SC, it was also similar. But in the case of SSB-SC, you can see that it's very complex process. There are a lot of Hilbert transformation, phase shifting, a lot of things going on. So it's actually a bit complex and also costly, difficult to generate. Then in the case of demodulation, in the case of DSB with carrier, we know that we can use both envelope detection and coherent detection. For envelope detection, the condition was mu less than or equal to 1, and coherent detection can be used regardless of the value of mu. But in the case of DSB-SC and SSB-SC, envelope detection is not possible. Now, power efficiency. DSB with carrier had a power efficiency of 33%, which was very inefficient, but power efficiency is increased in the case of DSB-SC and SSB-SC. Now, bandwidth requirement. DSB-WC and DSB-SC both required twice of the message bandwidth, so they were bandwidth inefficient. But SSB-SC, in this case, bandwidth requirement is equal to the message bandwidth, so this is called bandwidth efficient. Finally, we have reached the end. This is actually the end of AM. In the next sessions, we will talk about frequency modulation and other different type of modulation technique. Till then, goodbye.